Okay, everyone. We need to talk a bit about how bright stars are, because there's some things that lead us to have issues with just looking at them, right? So you can't just look at a star and tell if it's brighter than another star. Um, there are differences between them, right? First of all, the star itself can put out different amounts of light. Uh, the size of the star absolutely matters. So a bigger star tends to be brighter than smaller stars. And how far away we are from that star matters as well, because how far away we are determines how much light we see, right? And you can see that even just in a car. If a car is really far away, the headlights look dimmer than if they're right next to you. Okay, so the distance matters. So there are two ways that we essentially use, or we talk about the brightness of stars. One is what's known as the apparent magnitude, the other is known as the absolute magnitude. Now, the apparent magnitude is what we use to essentially quantify how we see the stars, right? How we see the things in the sky. Okay, um, so we use this to essentially compare them visually, right? So the apparent magnitude, how does it appear? How bright does it appear to be? Um, these go in numbers. They range from big negative numbers to small positive numbers. Um, so that a first magnitude star is actually 100 times brighter than a sixth magnitude star. And there are essentially 5 uniform divisions in between. Okay, so you can see here, for something at about a 0 of apparent magnitude, you're going to get which is something like Sirius, the brightest star that you can see. So not the sun. There's the sun somewhere up around negative 25. If I remember correctly, it's really like negative 27.3. The moon, on a full moon, somewhere around negative 12. Okay, those two are the very brightest things that we can see. Okay, and if you look way down in the dim objects, you see things like Pluto when it's really far away. I'm sorry, Pluto at opposition, which means it's the reflecting all of the light that it can from the sun. So apparent magnitude has to do with how we observe them, which one appears to be brighter. The absolute magnitude is defined in a slightly different way, but it's essentially defined based on a standard distance, and that standard distance is 10 parsecs. So 30 some odd light years. How bright would that star appear to be if you were that far away from it? And in the case of the sun, right, the apparent magnitude is really, really bright, negative 26.7. Okay? Absolute magnitude, much smaller, because if you're 10 parsecs away from the sun, which is pretty far away, the sun is going to appear to be very, very dim. Right, now, another way that we measure the brightness of stars, and basically a way that we rank the brightness of stars, is what's known as the luminosity. Okay, the luminosity is related to the absolute magnitude, and it's essentially just set in units related to the sun. So is it, 10 times as bright as the sun, or 100 times as bright as the sun, or a tenth as bright as the sun? Right? So we measure those units in terms of solar units, essentially. We compare the brightness always to the sun. Now, stars in general all have a different peak frequency, and that peak frequency is kind of what you're looking at the peak of these particular lines here. Okay, so a hotter star is going to have a peak frequency that's somewhere in maybe the ultraviolet range or in the violet range of the spectrum. A slightly cooler star will have a peak around the green region, and an even cooler star will have a peak around the red region. Okay, so when we see these stars, you're going to see color variations where some stars will appear to be red. Those will be the cooler stars. Some stars will appear to be bluish. Those will be the hotter stars. And the ones in the middle, though we refer to them as, we call it yellow. To us, the sun looks yellow. Superman gets his powers from the Earth's yellow sun, but the sun is not yellow. Were we to view it outside of the atmosphere of the Earth, the sun would appear to be white. Okay, and you're going to see that in the video, the Crash Course Astronomy video that I posted. Another super interesting thing about the sun is that although it appears to be whitish, yellowish, orangish, depending on how and when you look at it, its peak frequency, it's one of these basically 6,000 Kelvin stars, right? Remember, the surface temperature is about 5,800 Kelvin. The peak frequency for the sun lies in the green region of the spectrum. But because of the way our eyes see, the sun doesn't look green. Okay, we see, though that peak is here, we see all these different colors all at once, so it appears whitish. Okay, we lose a bit of the darker blues and purples because they're scattered by the atmosphere. So when you look away from the sun, you see every color but orange and red and blue. I'm sorry, orange and red and green. So you see blues and purples. So the atmosphere controls how we see the sun, okay, and our human bodies control how we see it. Okay, if we only saw that peak frequency, the sun would look green, but we don't. We see everything else with it. Okay, these curves here are what's known as black body radiation curves, and you're seeing the peak frequency. Everything at some temperature is going to radiate some amount of electromagnetic waves, right? Humans and things, we're at a much lower temperature, and so our peak frequencies lie in this infrared range. But we're still emitting electromagnetic waves in the form of heat radiation. Now, we classify stars based on their temperature from the hottest to the coolest, and we use these letters, OB, AF, GKM. Okay, they're just letters that tell you something about the temperature of the star, as you'll see in just a minute. Okay, so here are essentially the different temperatures. O's are the hottest stars, right, and M are the coolest stars. And then the orange, red, yellow, that's where the sun falls. Okay, the letters do not really match up to what's there. Right? And then notice there's the white, right at the cusp where the sun is. So using the sun as basically a standard measurement, we can then take everything we know about all the other stars and we can plot them. And what you find is that if you plot the absolute magnitude of the star versus the temperature of the star, right? So the spectral type is the temperature, O, B, A, F, G, so on. Okay, and notice here the temperature goes up, so it's the temperature scale, same thing as the spectral type. What we get is this nice little line here, and this purple line is what's known as the main sequence. And almost every star, as it's born, as it's going through its normal life, almost every star is going to be somewhere at or near this main sequence. Okay, outside of the main sequence, we have much larger supergiant stars. Okay, one of these that's really interesting is Betelgeuse. This is one of those ones that flicker at night. The reason it is interesting is that at any point in our lifetimes, it could supernova. And if it does, it will be bright enough to where it'll almost look like there are two suns in the sky. Right? It'll be bright enough to shine throughout the night. The thing is, it could happen in our lifetimes, it could happen 7 lifetimes from now. We know that it's close to the end of its life, but that's about all we can tell because it's so far away. So it's hard for us to figure out when that thing might go off, but it could be in our lifetimes. You might have 2 suns one day when you wake up, and it'll be because Betelgeuse supernovaed, and the light finally made it to us. Scientists are pretty sure it's already done it. It's just a matter of when and when's that light going to get here. You also have down here, these are your white dwarfs. These are essentially the leftovers of older stars, okay, that don't have something else happen to them. Okay, and then you have what are known as Cepheid variable stars. So these stars are really, really interesting because they'll pulse light at known intervals. And so we can use that to measure distances to certain places in the universe. And then from there, figure out how far the stars nearby actually are. So here we kind of talked about the life of a star already, right? The gravity collapses it, all the density and temperature and pressure causes essentially the helium atoms to fuse. At some point, the process of fusion, nuclear fusion is what occurs in hydrogen bombs, right? And the atomic bombs at the end of World War II, those were fission bombs, which means they were splitting atoms. Newer hydrogen bombs fuse atoms. It generates the same amount of energy as you would see on the sun. The first time they tested one, they vaporized an island and almost killed the people who were testing it because they didn't know how big the shockwave would actually be. There's a neat trick to how they do it. It's just using an old fission bomb with some hydrogen gas in it. Anyway, the fusion generates a lot of energy. And so it pushes outwards on the star, but gravity pulls inwards. And eventually, those two things will kind of fight each other, but eventually they'll reach a balance. And the star will maintain its size at that point. It won't collapse anymore, okay, because the outward force of the fusion is keeping it from collapsing, but it also won't explode and spread out because gravity is keeping it together. And so you get a dynamic equilibrium between the two where these two forces balance out. And at that point, that's when you have a main sequence star. That's when it's going to start burning fuel just like main sequence stars do. And so here you can kind of see an image of that, right? So inside the core is the fusion pushes outwards, gravity pulls inwards, and you reach a balance point. That balance point exists until the star starts to run out of fuel. That's where interesting stuff happens. Now, as stars evolve, they'll essentially move along that HR diagram. This is the HR diagram, okay? It's called the Hertzsprung-Russell diagram. You'll never hear me call it this. You'll hear me call it the HR diagram. Okay, but as stars age, they will move along here. Now, through most of their life, they'll spend most of their life on the main sequence. What happens is towards the end of their life, where things can be different, where you start to see different stars have different outcomes. Okay, at some point in every star, the hydrogen fuel runs out. All that hydrogen is now helium. Okay. When that happens, the core will collapse a little bit. Okay, and it'll heat up, and the outer shell of the star itself will start to cool. Okay, that disrupts that balance between the thermonuclear fusion, which isn't releasing the same amount of energy anymore. Okay, the star will still wind up fusing helium into carbon, regardless, but you lose that balance, and so the star starts to swell. And as it starts to swell, you get what's called a red giant. What happens after a red giant is then dependent upon the star itself, particularly how much mass the star is made out of. Okay, hotter stars, as we talked about before, those O stars, they're only going to live for about millions of years. M stars, the coolest stars, will live for trillions of years. Okay, there are some M stars that were formed at or near the beginning of the universe, and will exist well beyond it. The universe, to our understanding, about 13-ish, 14 billion years old. Okay, those M stars will live for trillions of years. So they could have formed at the beginning, and they're still very much alive. But this is the important thing to remember about stars in general, especially about how stars evolve, is that the mass of that star will ultimately determine what happens to it.